which is this term. Eliminate by subtracting 0.1 times the first row. Okay, subtracting 0.1 times the first row from the second row. Okay, means 0.1 divided by 1. Okay. Okay, if you notice the difference between Gauss-Jordan and Gauss elimination is the normalizing of the first element to make it equivalent to 1. Okay, whereas in Gauss elimination, you don't normalize it so that the first element here is equivalent to 1. The reason we did normalize it is because at the end, we want the matrix to be in this form, 1, 1, 1. We need the unit matrix. Okay. So that's the reason at the very beginning, the first step is to normalize the by divide with it by itself. Okay. And then the subsequent step is just a normal Gauss method. That means we need to make this element here 0, like that. Okay. And then the next step is to make this element just a method alone without Jordan. Then if you normalize 3 become 1, that's not correct. Okay, even though you will get the correct the answer is correct, but it is not part of the calculation involved in Gauss elimination, so it is not considered to be correct, because as I told you, when you solve problem using Gauss elimination, okay, at the end of the calculation, your matrix must be the same as your friend's matrix. Okay, there is only a unique answer to that, unless you perform partial pivoting. Then you change the row become column, first, second row become first row, like that. Otherwise, if no pivoting is, then the final, the last matrix should not be different from your friend. Okay, so this different, even though the answer is correct, then that is not the method that you carried out actually does not comply with Gauss method. As simple as that. Okay. So even when I ask a question on Gauss, you got a correct answer at the end, it doesn't mean that you get a full mark, because I will check the matrix that you get at the final stage whether it is correct or not. Okay, so but don't worry, the marks deducted will not be a lot. Okay, as long as the answer is correct, you still get marks. Okay, going back to this calculation here, so what is need to be done is just to, every time you arrive at this particular stage where you got the 0 element there already, then you start normalizing the second row, second element to become 1 by dividing itself throughout the row. Okay, next you make this one 0, like that. After doing that, then you divide this element by itself to make it 0, and then to make it 1, sorry. And then perform further calculation Okay, the x3 term can be reduced and the second to give. Okay, so the last step is to make this element 0 by using the x3 terms can be reduced from the first and second equation so that it becomes 0 to give here this number. So you are using this as well to get this element 0. And this element 0 also you will be using this by doing the elimination method. Okay, so you practice it. So what Gauss-Jordan did is to get all the mean diagonal become and also to make this element 0. That is the additional effort introduced by Jordan. Okay, so that is the end of chapter 9. Okay, next I'm going to move on to the next chapter, which is chapter 10. Hold on for a while. I'll to you. Okay. So students are okay. It's on what we call as LU decomposition. L means lower triangular matrix. U means upper triangular. So what is lower triangular? Lower triangular is a matrix where, let me show you. Okay, this one is upper triangular. You see, the element below the main diagonal are all 0. These are called upper triangular. So lower triangular is this one. Oh, sorry. This matrix. Okay. Okay, the element above the main diagonal is 0. The main diagonal doesn't have to be 1, all of them. It can also none and still is called lower triangular. Okay. As long as element above the main diagonal, that is called lower triangle. LU decompose here means you segregate, decompose. Okay, now what is the advantage of LU decomposition method? This method separate the time-consuming elimination of matrix A from the manipulation of the right hand side B. Okay, so they give you shift in time. Okay. Save time by doing the matrix. Okay, system or linear equation like Gauss elimination method. We solve system of linear equation. So other than Gauss and Gauss-Jordan, we have another method. We call it Slu decomposition. Okay. How does this method work? Okay. We start with a matrix. The system of linear equation can be written in matrix form lah. Ax equal B. It become Ax minus B equals 0. Bring B to the... Suppose that could be expressed as a triangular system. Upper triangular multiplied by x equal D. Okay, that means U x equals D. Okay, that D left hand side Ux minus D equal 0. Okay. Now assume that there is a lower diagonal matrix with ones on the main diagonal as shown here. L equal 1, 1, 1 in the middle and then 0 on the upper element. And let's assume this lower triangular matrix that we create has the property that when equation 10.4 is pre-multiplied by 10.2, okay, sorry, is multiplied by the lower triangular matrix. Okay, that means you pre-multiply like that. L from the left hand side, you multiply the left part of the equation. Okay, Lux minus D equal so you by Lux minus D equal Ax minus B. All right. So let's assume there exists a lower triangle that behave in this manner. So if this is achievable, then we can follow the rule of matrix that Lu will be equivalent LD, L multiplied by inside, bring it inside, equivalence to B. Okay. A two-step strategy for obtaining solution can be based on equation 10.4, 10.7 and 10.8. Okay. So that is the step involved in Lu decomposition. These are the steps involved in Lu decomposition. Number 1, Lu decomposition step, we call it. Okay, so first we have LU decomposition step A. A is factored or decomposed into lower and upper triangular matrix. Step number 2, substitution step. L and U are used to determine a solution D by forward substitution. Then the result is substituted into equation 10.4, which can be solved by back substitution to obtain the unknown x. Okay. Now let's show how Gauss elimination can be implemented in this way. So these are the flow chart involved in LU decomposition. Okay. Okay. First, A is being decomposed into upper and lower triangular matrix. Okay. So we call it decomposition process. And then after whole part of the matrix, you multiply with the unknown matrix D, equally bring the B on the right hand side of the original equation to be the right hand side of the LDB equation. Okay. So the unknown here is D. Okay. So D is can be by using forward substitution because this is a lower triangular. Okay. So you can use a forward substitution to solve for D. Having the value for that D will be the right hand side of the equation U. You bring it from the top, multiply by X, which is the unknown we are trying to find, and then equate it equivalence to D. Okay. So we just apply, because this is upper triangular, so simply apply back substitution to get 4x. That's how the step involved in this LU. And the advantage is just now stated here. It separates the time-consuming elimination of matrix A from the manipulation of the right-hand side B. Okay, so instead of manipulation of the right-hand side B like what we did in Gauss, we don't manipulate it. However, matrix A is we are focusing to decompose it into L and U. Okay. Instead, you are able to save computer space while doing the computation using software, because the LU matrix where the elements are all zero at the designated place can be temporarily being used during the computation to store element, and therefore the space of the computer of the memory can be significantly reduced. Okay, we're talking about solving hundreds of engineering equations. So if we have a big a big size of matrix, okay, you will need a lot of memory space, and memory and also the space with computer system. So if you use this method, the space can be psi 0 in the lower and upper triangular matrix. Okay. Okay. So we in the process of decomposing the matrix A, okay, we are actually employing the technique of Gauss as well. Gauss elimination can be used to decompose A into L and U. This can easily seen for matrix U, which is direct product of the forward elimination. So example is this one, upper triangular matrix. And this matrix is typical of matrix involved in Gauss elimination. So recall that the forward elimination step is intended to reduce the original coefficient matrix A to the form of upper triangular matrix. Though it might not be apparent, matrix L is also produced during the step. This can be readily illustrated for a three-equation system. Okay, so these are the system of equation. The first step in Gauss elimination is to multiply row 1 by the factor A21 divided by A1. Result from the second. Similarly, row 1 is multiplied by F31 equal A31 over A11, and the result subtracted from the third row to eliminate A31 so that it becomes 0. Then the final step is to multiply the modified second row by F32 equal A prime 32 over A prime 22 and subtract the result from the third row to eliminate A prime 32 so that it becomes 0. Okay? Now suppose that we merely perform all this multiplication, manipulation and matrix A. Clearly, if we do not want to change the equation, we also have to do the same to the right hand side, which includes B, right? But there is absolutely no reason that we have to perform the manipulation simultaneously for this LU decomposition method. Therefore, we can save the F and manipulate B later. Okay. Where do we store the factor? Where do we store the factor F21, F31, and F32? Recall the whole idea behind elimination was to create 0 in A21, A31, A32. Thus, we can store F21 in A21, F31 in A31, and F32 in A32. So that's what I'm telling you just now. Okay, this particular storage is very useful when we deal with computer calculation. So after elimination, the A matrix can therefore be temporarily written in this form. Okay. We actually utilize the space temporarily without having to store two matrices. Just one matrix is being focused for storage. So it represents an efficient storage of the LU decomposition of A. So A, we decompose it into L multiplied by U, where U is the upper triangular matrix and L is the lower rectangular matrix in this form. Okay, now the following example confirm the decomposition of A into L and U. Okay. Question there. The question is derive an LU decomposition matrix based on the Gauss elimination performed in example 9.5 for matrix A. Okay. So this is the matrix A. So now we are going to decompose it into L and U. Okay, the U matrix is obtained by using forward elimination as we did in Gauss method. Okay, same exactly we apply the Gauss method to get the upper triangular matrix. All right. So the number that we obtain in the upper triangular matrix, now the following step is to create the lower triangular now. Okay. So in order to create the lower triangular, we use the number employed in the upper triangular matrix. Okay. So the element A21 and A31 were eliminated by using the factor F21 equal 0.1 divided by 3 and F31 equal 0.3 divided by 3, and the element A prime 32 was eliminated by using the factor F32, which is minus 0.19 divided by 7.00333, become minus 0.027130. The prime there indicate the second step obtained in the process of doing the calculation. Okay, if double prime means the second step involved in the calculation beginning from the original matrix. Okay, and if it is triple prime, it will be the third matrix that we produce, the element from the third calculation of the matrix. Okay, so the lower triangular matrix thus will be the F21 element. Substitute here. 21 means second row, first column. F31 means third column, first column. Okay. F32 means third row, second column. Alright, and then put 1, 1, 1 in the main diagonal. So now we got A being decomposed, and if you multiply L with U, you get the matrix A. Okay, but we have some discrepancy in the numbers due to runoff approximation, due to runoff explanation, because just now the original metric is 0.1 here. Now you've got 0.09999. Here it's 10 just now, but it's very close. The number are very close to each other, but the slight difference is due to the runoff error. Okay. Okay. As a continuation to that, we are going to continue with the LU decomposition that has been done on matrix A is now to solve the simultaneous equation. Okay, so this is the continuation of the calculation. So this is matrix A times X equal B, and we use the forward elimination using the conventional Gauss elimination method, you get this matrix. You see, even though this matrix is undergoing Gauss, but the B will also be going through the same process because conventional Gauss apply both right and left and right hand side calculation. However, the forward substitution to get the lower is carried out by applying equation 10.7, and this is the result that we got, which is from here. Yeah, see, same. Okay. So we multiply with unknown element D equal B. Remember just now I told you the flow of the calculation. Just stick to this L times D equal B. So the D can be solved by forward substitution. Okay. What does forward substitution means? Forward substitution means you have x1 equal 3 like that. Forward substitute. Okay. And then we have 0.0333 x1 plus 1 times x2 is equivalent to forward substitution. 1 times d1 plus 0 equals 7.85. So we can solve for d1. And then 0.03333 d1 plus 1 times d2 plus 0 times d3 equal minus 19.4. So having got the value, you can substitute it inside the second equation to solve for d2. That's called forward substitution. And then from the last equation, so remember the D goes to here. Here, it goes to here. See the D here, which become the right hand side of the upper triangular multiplied by x equals D. Understand? And then from there you can readily solve for x by using backward substitution. Okay. So this D become the right hand side of ux equal D. And using backward we can solve for x. What does backward substitution mean? That means we solve the lower line using the xt number, solve for x2 here. After getting first row, so that's called backward substitution. We start from the bottom going up, backward. Okay. Forward means we start from the top going down, forward substitution. Understand? Okay, in terms of algorithm, this is the computer step involved in the Slu decomposition technique. Okay. Okay, we can apply the matrix Slu decomposition to find the inverse of a matrix. Okay. So in order for a matrix to be inverse, it must be a square matrix. Okay. That means the inverse is labeled as A to the power of subscript -1. Okay. So the A multiplied by the inverse equal identity matrix. Inverse multiplied by A also we got the identity matrix. Okay. Okay, how to use the LU decomposition to find the inverse matrix? The inverse can be computed in a column by column fashion by generating solutions with unit vector as the right hand side constant. For example, if the right hand side constant has a 1 in the first position and 0 elsewhere, the resulting solution will be the first column of the matrix inverse. If a unit vector with a 1 is positioned at the second row, then the result we got will give the second column of the inverse matrix. Okay, and so on. If you put 1 at the last element, then the third row will be the third column of the inverse matrix will be the resulting solution from the equation of having 1 in the last row. Okay, example. Here, example. Now, we want to find the inverse of this matrix by using LU decomposition. Okay, first, we decompose the A into L, U, and L. Okay. Then, the first column of the inverse matrix, that means the first column of the answer of the matrix that we are trying to find, can be calculated by performing the forward substitution solution procedure, having unit vector. What is a unit vector? 1 in the first, the right hand side vector, like that. Okay, so set it equivalence to 100, and then we use forward substitution. Forward means we start from the top, go to the bottom, go to the bottom. That means forward. So we use forward substitution to get D1, D2, D3. Okay? So this is the answer. So this answer constitute the right hand side of equation 10.3. Okay? That means we have upper triangular multiplied by x is equivalent to the right hand side. The right hand side is the answer for the D that we got just now. Understand? Okay, here, there, this one. So this is transpose. T means transpose. Why do they write it in transpose form? Because they want to save space of the book. If they put it in the column vector, then it will, we have space problem. So we put it in a line form and put a transpose there to save space. Okay. So we saw for x here, and the x that we got is making the first column of the inverse. The step involved is the one that you need to understand. And then the other two remaining column, we temporarily put a 0 there. Okay. All right. Now we are going to eliminate this 0 for the inverse matrix with some numbers. How do we do that? Okay. We just do the same thing as we did in the first step here, but we change this one to 0, 1, 0. One at a time. First we use 1, 0, 0, and then 0, 1, 0, and then 0, 0, 1. Okay. So we use 0, 1, 0, and then we use forward substitution. We get your D. Okay. After we got the D, just like before, but they don't show you the detail now. So that become the right hand side, okay, of the x1, x2, x3, which constitute the second row of the inverse matrix. Okay. So just cut short without showing you the step-by-step calculation anymore, because it's already shown on the top there. So the answer to this D will constitute the right hand side of the upper triangular multiplied by x, and the x will be the second column of the inverse matrix. Okay. So the third column of the inverse matrix is obtained by setting this now become 0, 0, 1, and solve for D. After getting the D, make it the right hand side, like here, make it the right hand side of the upper triangular multiplied by the x, where the x now will be the answer for the third column. So that gives you the inverse matrix. Previously, how did we find the inverse matrix? We use adjoint, okay, and then we use what? We change the column become row, row become column. Okay. In front of the matrix, we multiply with 1 over the determinant, if you still remember. So now is using the Slu decomposition technique to find the inverse matrix. Okay. Okay. Now special matrix and Gauss-Seidel. Okay. But the scope for this part is only on Gauss-Seidel. If you want, Cholesky is not part of the scope. Okay, so Gauss-Seidel. Okay, so the Gauss-Seidel, I'm going to talk about it in my next lecture, which is on Thursday, yeah? Wednesday. Next lecture. Okay, Gauss-Seidel, remember. Let me check. Confused about the date. I think it's on Thursday, right? 2:30. Okay. Okay, correct. Thursday to 2 p.m. Sorry. Okay. So those who already get the code from the email, you need to install it. I give you, it's not as difficult to install it. We're gonna take not more than 15 minutes actually to register the code. So I give you until tomorrow, and that means you need to install it tonight and also morning, because in the afternoon tomorrow I start upload the question and the assignment and the quiz. Not the quiz yet now, only the assignment first. Okay, with the beginning time and the ending time that you need to do. Okay, so if you install or you register the code after I upload the question assignment, I'm worried that the assignment will not be captured on captured on the person on those who register late after my uploaded file. They will not get the question. So make sure by noon tomorrow, everyone who got the code already register. Okay? So there are 5 students who already WhatsApp me that they didn't get the code. So you just have to wait for a few more days for me to receive it, because although some of you might have paid it early, I'm sorry, because I'm one or two of you might skip. I didn't. I skipped. That's why I want to counter check those who didn't get the code to WhatsApp me. Okay. So don't worry for 5 of you, even though you might miss the first assignment. I will take the total excluding that particular problem for your total mark. Okay. But life has to move on, so I have to start upload it by noon tomorrow. Okay. So we are going to extensively using the piece, and you will have to focus on how to use it and learn how to use all the what we call information they gave inside the video in order to study for the subject. Okay. So you have any question? Okay, by the way, if you notice the ebook, you try to do some searching there inside the website. You will be able to get the ebook. Okay, the text, the cover of the book is orange in color. Orange, like the color of the traffic light. Orange. Okay. Now, I have for those of you who wants I only have 3 copy, the hard copy I offer some discount, but I have only 3 of them. In case any of you want it, I offer the lowest cost ever had offer, which is including shipping is 85 ringgit. Okay. I think you will never able to get that anywhere. I think so. If you can get it anywhere, you show me. I will offer less than that. But as far as I know, 85 ringgit, including shipping, will be the lowest price. But I just need to. But I only have 3, so 3 copies. Those who want it, first come, first serve lah. Okay, it's not compulsory Those who have maybe one got A and study by having hard copy, get it from me. Okay, but you can still get it. Any question now? Okay, so make sure you learn how to operate that code and also access all the what we call information, problem, e-learning from the website. Okay. Any question now? No question, Are you still with me? Okay, I'm going to download the attendance now, so make sure you don't log out first. Okay, wait for a while. I'm going to download your attendance. Hold on. But those of you who still want it, you can, time is open. Okay, you can still pay and then wait for me to email, but it won't take so long because those who maybe about 3 to 5 days like that, you will get it. You can still order it if you want. Okay, hold on. My computer is buffering and little bit slow here for me to get the upload button. Okay, now is wait, attendance report. What have I okay, wait, okay. Participant download attendance list. Okay, it's in the process of downloading. Okay, it's already download. Oh, okay guys. Have a nice day and siapa yang puasa tu selamat berbuka puasa. So see you again and bye bye.
Thank you, Mr.
Bye bye guys.
Thank you, Mr.
You're welcome.
Thank you, Mr. K. Thank you, Mr. K.
You're most welcome.
Thank you, Mr. K.
Thank you, Mr. K.
Welcome.